হচ্ছে ওই পালিশ ম্যাট্রেস হবে এখানে ওই ব্যাগ আমরা ওখানেও বইতাম, ব্যাগের জন্য এখন কেন ব্যথা ম্যাট্রেসের পালিশ এই দুটোর জন্যই আমাদের যদি পিঠে একটা বালিশই নিয়ে নেবেন, মানে একটা বালিশই করে নেবেন। বালিশ চলে আসছে কত ঘুমাবে নিয়ে কি করে কাজ করে ম্যাট্রেসটা বেশি দিতে হবে। ওই জন্যই তো ঘাড়ের সমস্যা হচ্ছে।
Oh yeah, I saw the email because I submitted on cameras and asked it's just a little lengthy. Oh yeah. Oh, the one was I was used.
No, all of them are from
Is just
most of them. Derivation? Yeah, those are mostly from GPT, but every step I can convert it's again. I have done 5, but 5 is good. Today I'm going to maybe today. Yeah, today I'm going to finish. Anyway, we have it until 26. You saw the number 8. Yeah. That seems actually I understood all of them like from top to bottom. You know how long was the derivation? It was this long because this conversion of dx into du was like. I took u as a.
not
Yes.
Yeah.
Yes. But in between there was an intermediate. Yes. I didn't mention
those ways is next on. Yeah, or you can mark it.
I have one as well, so if you want.
Basically,
I have one.
but just make sure you bring it with you.
Okay, okay. Actually, I replaced.
Who want another one?
I replaced this.
Which one of you want another one? Probably give that to you. Okay, remember to take that with you every time, okay? I have another one. Who want this one? Okay, you laugh the most. So this is the target.
I have, Professor, I have. Okay, so I'm ready.
Remember to take that with you every time, okay? I have another one. I have another 6.
I don't understand anything, so it's better to laugh, right? At least it will be helpful for my health, so.
Okay, so where we stopped last time? We finished the derive of the entropy, right? So, and we also mentioned that the entropy basically is the k times ln the number of the microstates under a given distribution, correct? So I think we still have some important task. I have not done it, but I will spend about probably 10 minutes to finish the job, and then we can move on to the next chapter, right? So at the end of last time, we mentioned Bs actually is equals to dk times the ln omega. Okay, omega is the number of microstates under a given distribution. Okay, so this is the now. And to be more specifically, the S equals to N is the number of particles times K times and sigma I and Ni ln omega I minus sigma I Ni on Ni minus K on. Okay, so actually this term make the particle indistinguishable. Okay, because we are treating the identical particles. So that's the definition. Okay, right. Basically this is a correction. This is a correction for the Boltzmann distribution. Okay, so anybody can tell what's the equation on the others? What's that equation?
Right.
Huh? What? Okay. It's not I did not write it. Just a quick test. Just a quick test to see whether everybody knows what that. Okay. Anyway, so let's come back. All right. So this is basically what we know. Okay. So then the question is, we spent a lot of time just to link the microstate to the thermodynamic parameters. Okay. But how can we use them? Okay. So for example, how can we calculate the entropy of the ideal gas? Okay, and whether, if we know the microstate distribution or the microstate states, in principle, we should know all the information of the system already, right? The question is, if we know this distribution, whether we can establish all the equations we already mentioned. For example, like PV equals to nRT, for example, the definition of the energy, entropy, whether we can rebuild through this pathway, okay? So this is something we're going to talk about. Let's spend a little time to talk about it. Can you read that one? I think 2, what did we talk last time? This is section 6. Okay. Functions, not functions. Okay. Equations. 5 equations. 4 ideal gas. Okay. I just give you a few examples, but we cannot derive all the equations, but few examples. We don't have that much time, okay? So first of all, let's see whether from that kind of the microstate to get this equation, okay? Okay, whether we can get from this equation. Remember, we define the partition function, right? So that partition function is what? Is that correct? It's the partition function, right? And then from it, we derive something like this. So this is what we have from the last week. Okay, so if you don't remember, just check the. Oh, by the way, so the homework is due this Friday. Okay, the first homework. Okay, I only received 2. But I'm not receiving other people's. Okay, remember, I still prefer you send me the homework by email. Okay, but if you did not send by email, you still need to drop me an email to remind me where I can find it. Okay. Okay. All right. So this is the definition. But in order to calculate the pressure, we need to calculate the partition function. Right? Partition function is defined now. Okay. So for the ideal gas, remember, for the ideal gas. We only consider the kinetic energy, right? So then the E equals to what? Is the Px, Py squared, Pz squared, right? Divided by 2m. Is that correct? And then the partition function will become it is not sigma anyway. So the we'll still write it anyway. That doesn't matter. So omega I E. We know beta, right? Beta is kT, right? 1 over kT.
Pressure or moment?
P is good question. That is pressure. Momentum. What should we do with momentum? Any other ideas and suggestions? We can change the expression to momentum. How can we change the momentum? Use another word. Use another letter.
H bar K.
Huh?
H bar K.
Nah, that's more complicated. Momentum. Momentum. Okay? Let's use this one. Mu x, mu y, mu z. Okay, the momentum. Okay, everybody agree? If you don't agree, that's fine, don't worry. Okay, this is something like this, right? So we need to sum all over all possible momentum. Correct, everybody? All possible momentum. But the question is, what about this one? What about the degeneracy? The degeneracy. So I think I mentioned it a long time ago at the beginning of the class, we talked about the momentum space and rho space. We talked about the ideal gas, right? We talked about the ideal, for example, if we have a tank of ideal gas, we just try our best to separate the small volumes, okay? Each of the small cube is corresponding to one state, or one quantum state, whatever, one energy level, whatever, right? Remember, we give this picture to you. And then each of this small part has a volume of dx, dy, dz. Correct, everybody? And then the question is how many of this small volume inside this large tank? we define something like this, right? H3. Correct, everybody? So, in that case, we can change that one to VH3. Okay? But on the other hand, we also need to sum across all these possible momentum. But remember, this one is energy. This one is momentum. But how can we link them to each other? Right? How can we link them to each other? And we already know that if we also draw the momentum in the xy state, the mu x, this is the mu y, this is the mu z. Okay? How can we find the particles with the same energy? Or in other words, they can have different directions. Momentum can have different directions, right? But they can share the same energy, right? The question is, how the particles with the same energy distributed in this momentum space? Look at this equation. That means the mu x squared plus mu y squared plus mu z squared equals to a constant, right? Equal to the same energy, right? If the energy is the same, so how the momentum distribute on this space? It's a ball, right? It's a ball. It's a sphere, right? Something like this, right? Everything on the surface of the ball have the same energy, correct? Have the same energy. And we need to sum across all this kind of place, right? We need to sum across all the entire space in the momentum space or in the energy space. Right? So in that case, well, we can count. In order to count that one, we need to count the small areas, right? We need to also consider small areas. So it is something like the d mu y, d. So this is some small areas, and then we need to change them into energy. But of course, this part is already energy, right? We just change it back. This one is already energy. But what about that one? So since since that one is a small ball, then we can change something like this. D mu x. I try to be very quick, okay? So if you cannot follow, just we don't have too much time. And this one is not very difficult for our class. So just go very quickly. So if you have difficulty to follow that, you're welcome to come to my office and we can discuss more, or you can just review the video. Anyway, so this is a small volume inside this kind of momentum space. And but this independent variable is E, but this here is a mu, right? So how can we unify them? So this part is a volume, right? We can change that one to something like this. 2 pi E squared D. Something like this. Hold on. Is that 18? Hold on. I think it's not necessary for us to do that. We don't need to change that one, actually. We can make the job easier. No. Forget about it. I can make the job easier. Still use that one. Still use that one. We do not need to worry too much about that one. Anyway, we don't worry too much about it. But anyway, we need to sum across all the possible momentum, right? It's covered the entire momentum space, it's covered all possible energy, right? But of course, this is continuous, so we change the sigma sign to the integration, right? But we have three variables, so we do the integration 3 times. Okay? We do the integration 3 times.
Are the dx's in the exponent or at the very end, not in the exponent?
The what?
Are they in the exponent? Or
Which one?
the d mu of x, d mu of y?
D mu x is from negative to positive. Infinity.
I just mean, is it included into the e to the power of all of that?
Yeah,
Or
yeah.
is it-
Yeah, exactly. But the thing is, we can separate them, right? We can separate them, right? So this is a constant. This is the degeneracy, right? But it's constant. We can put it outside the integration. Then E 2m kt mu x squared d mu x integration mu y squared 2 m kt. And d mu y. Integration 2 m kt mu z squared d mu z. Correct? You can see the structure on x, y, and z exactly the same, right? So we only need to calculate one and the other. Everything else the same, okay? So if we talk about the lower limit and upper limit, to be more precise, so this one should be from the negative infinity to the positive. Something like this. So how to do this calculation? I direct you the result, okay? So this type of the integration, we call it the Gaussian integration, okay? This is the Gaussian integration. This is Gaussian integration. So the result is square root of pi, okay? So we can do the same thing here. But if you're not familiar with that one, you can just check online, so you can just check something like we call it Gaussian integration. You'll find all information, Wikipedia, everywhere is there. You can find how to do this kind of integration everywhere. It's not very complicated. You just need some trick. Okay, we don't spend too much time to talk about the details of mathematics here. But anyway, I just tell you the conclusion. So the conclusion is something like this. 2 pi k t m divided by h squared. And each of the integration is exactly the same. Each of the integration gives exactly the same term. So you have something like this. Any questions?
Are they dot products, like the infinity, minus infinity to plus infinity integrations?
What do you mean by dot?
Like, is it multiplication?
Like the 3 integrate, when it was integrated.
Oh,
to
it's the
It's
order of
separated
3.
into-
It's the order of 3. Yeah, because each integration gives you the result, the square root 2 pi kt m. And you have
Yeah,
1,
so
2, 3,
basically-
then the other.
Yes, okay.
Okay, so before is a v times 2 pi kt m divided by h. Okay, this is the result. Okay, right now we have the partition function of the ideal gas. Then we can calculate something like this. We'll calculate the P, okay, the pressure. The pressure is what? Again, is N, is the NKT times partial V ln Z1, okay? So then we put this one back here, so it's NKT partial V ln V times the whole bunch of the something here. Okay, it's the 2 pi kt m h. But you will find that actually this part doesn't give you any contribution. Okay? If we do the derivative of the entire term, the result is very simple. That's it. Correct? Right? because this one ln V times this one equals ln V plus ln and this whole bunch of the items. But this one is not functional V, so if we do the derivative, it's 0. Then we only have 1 over V. And from that one, we have the PV equals to NK equals to NKT. Okay? And compare with the ideal gas function, so we have PV equals to nRT, right? Then we know the relationship. The K, the Boltzmann constant, is R divided by the F-Gallagher constants. Okay? This is the for the ideal gas. I mean, yeah, indeed. So from the partition function and the microstate distribution, we indeed can get the ideal gas equation. I give you homework, okay? Give you homework. Just remember, but I will announce the homework next week. After finish one, the second one comes in, okay? So I always hear students, oh, where's homework? Writing out homework comes in, okay? After finish one, second one, you immediately come. And then after you finish the second one, midterm. You can do this kind of practice, okay? I'm going to announce that in the homework as well, okay? So, but I write it down right now. You can try to do that in advance before the official announcement, okay? Homework. So calculate the entropy of ideal gas, okay? I can tell you the result, okay? The S is equals to, if we, I already told you the partition of the ideal gas, right? The partition function. But the definition of the entropy is something like this. Okay, this is your starting point. And I already mentioned what the partition function looks like. And then eventually, you should get the S actually equals to 3 over 2 times NK ln T, okay? And plus NK ln N plus 3 over 2 NK. You should get this result. You should be able to get this result, okay? This is the accurate expression of the entropy of the ideal gas.
Does this only apply for one atomic?
Yeah.
The secretarial equation.
Yeah. I mean, they are able to verify it, okay? But this is your job, okay? This is your job. Your homework. But before that, I can also tell you this is correct, okay? This is correct. So we can get this expression from the partition function, but we can get the same expression just from the classical thermodynamics, okay? Remember, I'll give you some time to finish writing it. Okay? To calculate the entropy of the ideal gas from this definition of the entropy. Calculate this one. Okay? But once again, entropy, we can also calculate the entropy from the what? From the first law of the thermodynamics, right? We know that the du equals to what? Du equals to what? Du equals to what?
Minus P.
Then I'm asking you guys, du equals to what? I thought you are discussing the okay? This is the first law of thermodynamics, okay? Okay, so we know this one already, right? And give me a second. So what does du for ideal gas? What's the u on the ideal gas? Remember your homework one? I asked you to prove something. U equals to what? Integration of Cv dt, right? Then du is what? Okay? Then what we have is the ds equals to cv p dt plus p dv. Okay? And then we can do the integration. Okay, we can do the integration. And then we have s equals to integration of the cv p dt plus, we use the ideal gas equation, okay? This is the p, this is t. And this one is what? We know the PV equals to what? Equals to N, capital N. Right? So then P is what? P is the NKT divided by V. So we have this one, NKT divided by V, but we have T there already. So then this one becomes NK divided by V. Correct, everybody? And then this one equals to CV ln P plus NK ln V. Okay, and of course we have the integration constant. Right? So what's the CV for ideal gas? 3 over 2 NK. Correct? And compare these two equations. So we have this term and this term, right? A little bit different from this term, but doesn't matter, because we can this one we can separate into n times k ln n v minus nk ln n. Okay, is a constant. We can put all this term as an integration constant. So basically, what I'm saying is, if you calculate entropy from the from classical thermodynamics, you roughly get the same result. But you cannot, but you don't know is the integration constant. But if you calculate from the partition function and the statistics, I mean thermodynamics, we know all the information on the system. So the integration constant can be, can be determined. Okay, this is absolute. We call this one is the absolute entropy. Okay. So this one is relative, okay, because we have the integration constant. Practice this one after you go back home, okay? What's your question?
Yeah. I always have trouble understanding natural log of t or natural log of v with dimension inside the natural log. Should I just not worry?
Dimension disappear. Dimension disappear. If you put any kind of vector inside it, the dimension disappear. There's no dimension.
Okay.
The reason is, see that one. What's the dimension of this term?
No.
So when you do the integration, if you get a log, it's something like this, right? Any kind of vector. dt is the unit of temperature, and the t in unit of temperature, right? So the unit just disappeared. There's no unit anymore, right? So in that case, the ln t, there's no unit for ln t, okay? And you can see this term is unit just CV. So what is the unit of CV? Joule per Kelvin, right? So what's the unit of the entropy? Also joule per Kelvin, right? So this term has no unit, right? Okay, so done. Do practice, okay? I mean, if you do not calculate by your own, so it's really hard to understand and to memorize the equation. Okay. But anyway, so we spent a lot of time on explaining the statistics. On your syllabus, I think we already delayed 1 week. But anyway, I think it's still very important for us to understand the fundamental principles. Okay? So we move on to the next chapter. What's the name of the next chapter? Fundamental equations and their relationship. So what kind of fundamental equation we already know? What the fundamental equations we already introduced. Fundamental equations, that means that, for example, like the NV equals to Pn, PV equals to nRT, it is a fundamental equation. It's not a fundamental equation, okay? Because it's only applied for the ideal gas. It's not a fundamental equation for the thermodynamics. For thermodynamics, we care about the equation that works for any kind of system, okay? Just like F equals ma. So we don't care about whether it's particle, whether it's ball, whether it's metal, whether it's liquid, doesn't matter. Okay, it doesn't apply to a specific system. So that was the fundamental equation we already introduced. The first law, right? This is one. Okay. Well, you know that the delta Q in the reverse process, the delta Q equals to TdS. So I just put it here. Okay. All right. So and then for ideal gas, not necessarily for ideal gas, for the PV system, okay. That means we only care about the pressure and the volume. It's not necessarily to be ideal gas. It can be liquid, it can be solid, doesn't matter. Okay, but we know that this one equals TdS. Okay, it's not necessary for ideal gas, right? For the real gas, this equation also holds, because the mechanical work is only induced by the volume change. Correct, everybody? So this is for the PV system. And remember, we also introduced another concept we call is what? Entropy. Right? Why we introduce entropy? The reason is, for most of the time, we warm the solid or liquid or gas, warming it up or cooling down, the volume always change, right? So we have to understand, we need to calculate, or we need to do the experiment to monitor how the volume changes in order to calculate the change of internal energy, right? So we want to get rid of this term. How do they do that? Remember, how can we get rid of this term, the volume term? Because most of the experiments are performed under constant pressure, right? We want to make the job simpler. But right now, the volume is a variable. How can we get rid of the volume? Exchange the variable from the volume to pressure. How can we do the job?
Still remember? Introduce the total derivative of dP times V.
Yeah. Everybody else? Do you remember? How can we get rid of this term? Or replace the dV with the dP? We introduced another concept, right? Philippi? What's the definition of H? What's the definition of H? Entropy. It's not entropy, it's entropy. Because what? Correct? Why we define it that way? Because the dH equals du plus PdV plus VdP. Correct? And then this one equals to TdS minus PdV plus PdV plus VdP. And then the PdV plus and minus just cancel each other. And then we have the TdS plus VdP. Okay? So in order to get rid of the impact of the volume change, we can add a full derivative of the PV term and then change the variable from the V to P, right? To V to P. So in that case, for the constant volume process, if I inject or extract the heat from the system, the internal energy changes. For constant pressure process, if I inject or extract heat from the system, the entropy changes. Okay? The entropy changes. Then we have another equation, fundamental equation. Okay? This is the second one. Finish recording. put it down here. So we can use the du equals to TdS minus PdV, and dH equals to TdS plus VdP. Okay. All right. So you can see for this process, it's easier for us to use the internal energy. In the constant volume case, it's easier for us to use the entropy for the case of the constant pressure process. Correct, everybody? But you can see in both processes, the entropy changes, right? And I think you already know how difficult to calculate entropy is, right? Nobody wants to bother to calculate entropy. So can we change the variable from entropy to temperature? For example, this one is the as function of S and as function of V. Can we change that to the as function of T and V? Can we change the variable from S to T? How can we do that? Any ideas?
Can we use heat flow?
Huh?
Can we use heat flow?
Use what?
Heat flow.
No. I'm saying that mathematically speaking, not physically. So how can we change the variable of this equation from S to T?
Add another T times S term.
And another TS term? Everybody agree with that? Let's have a try, okay? We plus or minus. Minus TS or minus or plus TS. U minus TS or plus TS?
Maybe plus, I guess. Constant pressure.
Let's put a plus. Then the du, we do the derivative, okay? Du equals to TdS minus PdV plus TdS plus SdT. And then the whole equation will become 2 times TdS plus SdT minus PdV. You make the trouble more complicated. Plus or minus? Let's change the minus sign, okay? Minus, okay? Minus, okay? And then we cancel this term, okay? And then this one becomes negative PdV minus. All right, so what's the variable right now? It's V and T, right? It's not S and V anymore, okay? So we give this kind of term a definition. We call it it's A. It's really awkward. I think people have no letter to label this one anymore. So we give this A another name. What's the name of A?
Some sort of free energy, something like that.
Free energy. Okay. We call this one the Helmholtz range. Okay. And then we have another one. dA equals 2 minus SdT minus P. So this is another equation. Okay? And can anybody explain to me why we call this parameter alpha p? Can anybody explain that to me? Why we give this name, this kind of widget name? Anybody know? If you don't know, that matter, I don't know either. But if you feel interested, you can check online. But I know why, because it's free energy. Okay, I'm going to explain that. But right now, everybody knows the mathematical motivation of it, right? Why we define that? Because the homogeneous free energy is more suitable for us to analyze the constant pressure or isothermal process, because the T doesn't change, right? So in the isothermal process, this term doesn't change anymore, right? So it's easier for us to analyze the change of the system. That's the reason. Okay, so, but this one is just like mathematical argument. So what's the physics meaning of it? Okay, what's the meaning of it? The meaning is very interesting. Okay, let's go back to the very beginning of class. For the spontaneous process, if we only consider the kinetic system, okay, like the what's the treatment? I mean, you prefer stand or prefer standing or prefer sitting? You prefer lean on the bed or prefer to sit on the chair? Please stay in the bed, right? What's the reason for that?
Comfort.
It's more comfortable, right? Because their energy is lower, right? Everybody wants to have a lower energy, right? So that means the natural trend, energy wants to go down. Correct, everybody? We always want to sit, right? You can see even the pen wants to drop it, right? Okay, what about entropy? Entropy wants to go up or go down? Everybody wants to know, right? You prefer, which one tell me sitting is more comfortable than standing? Which guy said that? You said that, right? You told me that sitting is more comfortable than standing, right?
Yeah.
Okay. So, which way is more comfortable? A messy room or a very neat, clean, and tidy room? Make you feel more comfortable. Close the eye. Which one is more comfortable? Of course, a messy room because I don't want to clean up. Correct, everybody? Which one have really clean room? Let me know. Whose room is very clean? You can set down. My room is really clean. Okay, next time take the picture.
Yeah, you can go
Oh, thermodynamics is not for you guys. You disobey the natural law. But anyway, so the S typically going down, prefer to go up or go down. Go up, right? If nobody clean it up, you eventually become mess. Okay? Anyway, so these two process interaction or compete with each other, correct? And eventually, these kind of two factors give us equilibrium states, right? In that case, so U go up, S go down. So in order to find the final state, we need to combine them together, right? So definitely we need to have negative sign. With U go down, S, and negative S go down, okay? And then this kind of the expression should go down. That means for natural process, we need to minimize the value of U minus S. Correct, everybody? But there's an issue. They are in different unit, right? What's the unit of the energy?
Joule.
It's joule, right? What about the entropy? Joule per Kelvin, right? Oh, just add a T here. Make them the same unit. See that? They have the same thing. Okay. So basically, the physical significance of the homeostatic free energy is it tells us the trend of the evolution, the spontaneous evolution of the system. Okay, it's not to minimize the total internal energy. It's not to maximize the entropy. Instead, it's the competition between these two terms. We need to minimize these two parts of contributions. One from internal energy, the other is from how massive the system is. Okay, so this is the argument. I'm going to prove it. So we're going to prove it. Okay, proof. So consider. We have any kind of system, okay? We have any kind of system, okay, a system. It has some thermodynamic process inside the system. We don't care what it is, doesn't matter, okay? And then we have a huge reservoir at a constant temperature. For example, I'm teaching the class. You are recording what writing, probably thinking something what we're going to have for dinner tonight. Whatever, doesn't matter, it's your internal part. But the room temperature always constant, doesn't change too much, okay? Hopefully. But we just assume it's the constant temperature. Then, global point of view, if a spontaneous process is going to happen, the total entropy of the system should go up or go down. The total entropy is the sum of the system entropy plus the external entropy, okay? The total entropy for the spontaneous process should go up or go down for a spontaneous process. The total entropy go up, right? So So this one should be larger than 0. Okay, so for example, if we consider the volume of the system doesn't change, the volume of the system doesn't change, then what we have is the delta U, I mean, we know that the delta U equals to delta Q, delta U system, the system is the small subset, okay? Equals to delta Q minus P. Okay? And we assume that the system, we assume the volume doesn't change, okay? We assume the volume doesn't change. Why we do this assumption? Because definition of the free energy is a function of V. So if we assume the volume doesn't change, make the job easier. Okay? If we assume that the volume doesn't change, then we have this one, right? The change of the internal energy of the system equals to the heat got absorbed. Okay? So it absorbs heat from where? It absorbs the heat from where? From external, right? Then the delta S external equals to, it absorbs heat. So the external loses the heat, right? So we have the negative delta Q divided by T. Correct, everybody? Then we have minus delta Q divided by T plus delta system, delta S system. This one should larger than 0. Correct? And since the change of internal energy of the system equals to delta Q, what we have is minus delta U system divided by T plus delta S system. Correct? Then what we have is minus delta U system plus T delta S system larger than 0. Is that correct? Yeah. Or delta U minus T. Or delta A. That means for spontaneous process, the free energy tend to be minimized. For spontaneous process, the free energy always decrease. Because U decrease, entropy increase, but the minus TS decrease. Then the sum decrease. Okay? So for the spontaneous process.
Suppose from a very cold refrigerator,
About what?
from a very cold refrigerator or
Yeah.
minus 70, 80 degree, I keep that outside for some time. And it will warm up over time, right? If I keep it in the normal room temperature, it will warm up. It's
Yeah.
also a spontaneous process, right?
What?
It is also a spontaneous process.
Is the spontaneous
Warming
process.
up.
Yeah. Yeah, exactly. So basically, you put the S cube in the air. There is spontaneous process. Yes.
So there, if we calculate the entropy, it will be increased or decreased.
The entropy increases.
Suppose when it is cooling down, it is just releasing heat, right?
This release heat, but it did not release heat. It is absorb heat.
This absorption. So,
yeah, this warm up is absorb heat.
so if I keep a hot substance here, it will release heat
Yeah.
spontaneously.
Yeah, yeah.
If I take a cold object and keep it at room temperature, it will be absorbing, right?
Yes.
Two are opposite process, but both are spontaneous, right? one is absorbing heat, another one is releasing heat.
Yes, but that's the reason you have two factors competing with each other. If you only consider the entropy, they are in a different trend, right? But you also need to consider the internal energy also changes, right? And you can see that internal energy, one decreases, the other increases,
Yes.
right? So they are opposite way. So eventually they always reach the equilibrium states, okay? So we're going to talk about that again, and we're going to talk about the phase transition, okay? So you will see that the curve has some, eventually they will get some equilibrium cross sections, okay? I'm going to talk about very soon, okay? We still have time, hopefully we can cover that. But so far we only proved that for the home house, free energy is minimized for the spontaneous process, okay? But I have now explained why we call it free energy. Why it's free? Can anybody tell me why it's free? Huh? Why? Why the laughing? You still need to pay. Free. What's the funny point?
Without payment, we get it.
I hope that we can get some free energy. Okay. Remember, we're talking about whether we can make some, we call it the perpetual machine, that whether we can take the entire internal energy away from one system and then make them into work. Right? We're asking this question. And from second law of thermodynamics, we know that it is impossible to do that, right? Because we only need to have two heat sources. One is high temperature, the other low temperature, and we extract some heat from high temperature, and part of the heat changes into work, and we also need to release the heat back to the low temperature heat source, right? So that's basically second law. Okay? But the question is that then the second law told us it's impossible for us to take all the internal energy from the hot heat, from the single heat source, right? So this is what we're doing. Okay. Just to give you a reminder, okay? But right now, let's go back to talk what is free energy. Or in other words, how much energy we can eventually take from the hot heat source. Okay. Why we call it free? Let me see. So remember that from the first law of thermodynamics, remember the combination of the first law and second law. For the first law, we know this one, right? This is the first law, right? And for the second law, what do we know? Delta Q smaller than Ts, right? For the reversible process, delta Q equals to TdS. For the spontaneous or irreversible process, delta Q smaller than TdS. Remember? So we combine them together. So this is the first law. This is the second law, and we combine together. We have something like this: du smaller than TdS minus Pb. Okay. So this is what we have. Correct, everybody? Remember? Okay. So, from this one, we will know that this one. Okay, we just need that work. So from this one, we will know that the delta work is smaller than TdS minus T. Correct? And then that's minus. Okay, so let me explain what's the meaning of it. Think about it. We have a system, any kind of system, okay? At the initial state, we have the free energy A initial, and then it's output some work. It output some work. Then how the free energy change in the system. The free energy is TDS. How the free energy change? It's going down, right? It's the final. So then the delta A equals to what? AF minus AI. So this is negative stuff, right? This is negative stuff. So then negative A simply equals to AI minus AF, right? So basically change of free energy, but this one is a minus delta A is a positive stuff, right? That means the free energy got lost during the process. That means the energy or the work can be done by the system, or the maximum, equals to the change of the free energy. Equals to the change of the free energy. Equals to the change of the free energy. Correct? That is the largest amount of energy or work you can extract from the system. In other words, this part of energy can be set free from the system and change the form into the work. That's the reason we call it free energy. Okay, that's the portion of energy can be set free from the system. And the other part, you cannot take them out. Although the energy is there, but we cannot make work out of them. And only this part, and this is the maximum part, can be set free. Okay? That's the reason we call it free energy. It's not free of money. You know what I'm saying? It's not that cheap energy, or like we don't need to pay the invoice from the Duke energy. No, it's not mean, okay? It's not solar cell, okay? It's the maximum energy you can set free from the system, freely release from the internal energy. Okay, that's the reason we call it free energy. Okay? That's the reason. Okay, I give you the definition of the why we call it free energy. Any questions so far?
Yeah.
Why do you have so many questions?
I still want to ask.
Yeah, you do.
How do you get from the net line to W smaller than minus delta A? Like delta is not equal to.
Huh?
Is that term minus
Oh,
delta A?
Yeah, I mean, sorry, yeah, you're right. I mean, basically, I should add something like this. So basically, we do the integration. We do the integration on both sides. Okay, there's a gap. We do the integration on this one. And then we also consider isothermal process. The T is constant. So something like this. You know what I'm saying? For the isothermal process, the temperature doesn't change.
Oh,
Okay.
yeah, that makes sense.
Yeah, still, I mean, I forgot to mention, because this one is still isothermal process. Okay, the delta T doesn't change. We only consider the change of the entropy. But this is just an explanation of why it defines free energy. Because when I first learned the class, people my teacher told me this is free energy. I have simple question. Okay, you told me something to save money, but actually not. Anyway, so right now we know the significance of the homogeneous free energy. But honestly speaking, we'll talk about the phase transition or whatever in the future in the next few classes. We do not use the Helmholtz free energy quite often. The reason is the same thing. So for most of the physical process, melting the alloy and melting materials, putting alloys, and phase transition from liquid to gas, from solid to liquid. Typically, the volume change. Correct, everybody? It's difficult. We need to know the volume change. The question is, but all this process typically happens under a constant pressure, basically the atmospheric pressure, correct? We do not change the pressure, but the volume change. The question is, can we find some better parameter that change the dV to dP, make the job easier? How to do that job again? This is the third time I'm going to mention that one. How do I change the parameter from V to P? How to do that? Can anybody else give me an answer? Not you, but somebody else. how can we change the parameter from V to P? How can we change the V from P how can we change the V to P here? How did the result? Huh? What's that?
Enthalpy?
Yeah. How can we change how did we change the energy into entropy? How did we change that? What did we do? What did we do? How did we do make this kind of transformation? Check your notebook. How did we define the enthalpy from the internal energy? What's the relationship between the U and H? What's the relationship between U and H?
They're directly proportional, right?
Huh?
They're directly proportional because H equals E plus.
PV. Yeah. And what about this one? If I want to change V to P, how can we do? What should we do? How can we do that?
Substitute to work. You just do plus PVD minus.
Yeah, that's it. Okay? It should be louder. Okay? We find another parameter. Okay? Then dA plus, we do the full derivative on this one, is the dP times V plus V times P dV. Correct? This one equals to what? Minus T as dt plus PdV plus VdP plus PdV. Right? And these two terms cancel each other. This one is negative as dt plus VdP. Okay? Then we change the variable from V to P. Okay? And we give this one another name. What's the name of this parameter? This one calls the Gibbs free energy. Okay? This one is called Gibbs free energy. Okay, the difference between the Helmholtz free energy and the Gibbs free energy is if the system undergo a process under a constant volume, then we use the Helmholtz free energy to predict the stable state. Okay? In other words, if the system has a constant volume, we need to find the minimum Helmholtz free energy to find the equilibrium state. If the system has a constant pressure, then we use the Gibbs free energy to find the minimum or to find the stable state or the final state. You know what I'm saying? In other words, for the spontaneous process, okay, for spontaneous process. For spontaneous process. If P is a constant, if V is a constant, A is minimized, okay? If P is a constant, then G is minimized, okay? You know what I'm saying? In order to find the stable states, the final state, if the under constant pressure, we need to find the state corresponding to the minimum Gibbs free energy. If the system has a simple process and the constant volume, we need to find the minimum Helmholtz free energy. Helmholtz free energy. Questions? Questions, comments, concern? Complain. Something? Those don't always smell. So, any questions? Okay. Keep moving. We still have 7 minutes. So we have 4. These 4 basically we call them the fundamental equations of thermodynamics. Okay? And then we're going to talk about the Maxwell relationship. Okay, so for any kind of equation, x, y. Okay, for any equation. If this equation is continuous in the space, that means there's no abrupt change. Right? There's no abrupt change. Then we have partial square f, partial x, partial y equals to. No, let me write it in better. So we have this one: the partial x, partial f, partial y equals to partial y. Remember this conclusion? If fx is continuous across the entire space, then the second order derivative is independent of the order. Correct? It's independent of order. Okay, how to prove it? This is not my business. You're going to check your algebra, the calculus. But this is the conclusion. Okay? We apply this kind of mathematical conclusion to here. Okay? So we know u is a function of s and v, correct? Then from that one we will have partial s, partial u, partial v equals to partial v, partial u, partial s. Correct? Right, we just flip the order on S. So what is partial u, partial v? Partial u, partial v, partial u, partial v is minus p, right? And we have partial s minus p equals to partial v. Partial u, partial s is what? Partial u, partial s is t. Then we have the minus partial p, partial s as the constant volume equals to partial t, partial v, and the constant entropy. Correct? And you will also know the enthalpy is a function of S and P. By using that equation, we will have the partial T, partial P, partial V, partial S. Correct? And also we have A is a function of the T and V. We have the partial T, partial V. We have that one is the minus partial S, partial V, the constant T equals to minus partial P, partial T, constant volume. Of course, you have negative sign on this end, you have negative sign on this end. That's right. Okay. And from the equation G as a function of T and P, we have minus partial alpha b. Hold on, I think this should be positive. Here's a positive again. I made a mistake. Partial p, t equals to partial v, partial t. Okay. So they have 4 equations. 1, 2, 3, 4. Okay? Basically, they are the second order derivative of UHAG. Okay? But the second order derivative that independent of the order. So we can have, because of that, we have the following 4 relationships. So this relationship called the Maxwell relationship. Very important. Of course, if you know the fundamental principle, you can always derive. Okay? If you know, remember this 4 relationship, you can derive them. Okay? But what about if you forget about 4 relationship? At least you need to know the first one. Okay? If you know the first one, and you can replace the V with P, and then you got the entropy. Okay? And by replace S with P, you get the Helmholtz free energy. And by replacing V with P, you get the Gibbs free energy. Then you have the 4 relationship. This is the starting point. Okay? The following we just change the parameters. We just change the variables. Okay? By adding the full derivative of the PV term or full derivative of ST term, we can bring out all the following equations. Okay? And then you do the second order derivative, you've got all the Maxwell relationship. Okay? This is how you derive in case you forget. And there's another way to remember the Maxwell relationship. There's another way to remember the Maxwell relationship. Let me write down everything here again.
Excuse me, Professor. Did you change the sign of?
Yeah, I changed the sign. I just there's a mistake. Let me write the relationship. Partial T, partial V, S minus partial P, partial S, V, partial T, partial T. It's the 4 Maxwell relationship, okay? So each one have it. Okay? So the first one, how can we remember it? Actually, there's a chart. Okay? We can use, we have 4 parameters. We have 4 variables, right? S, T, and P and V. Okay? S and T is 1 pair, and P and V is 1 pair. Right? S, T corresponding to the heat, and PV is the work, right? So S and T is 1 pair, and P and V is 1 pair, right? And one thing is that remember the direction, okay? So we just define the positive direction from P to V as the positive direction, and S to T as the positive direction, okay? Just memorize it. That's the definition, okay? We just define this direction, okay? And then the relationship is like this, okay? P and S. Which parameter has a P and S as the variable? Which parameter has a P and S as a variable? P and S. The second one, right? That's the enthalpy. That's the reason I got really confused. This one is called enthalpy, this one is called mass. But anyway, so that's really annoying. So this is H, right? Okay. So in order to get a relationship, okay, we can do something like this. So, what should I do? Okay. So, anyway, so this is not very important. But anyway, so we can just draw a kind of a line. So we have something like this. Okay. See that one? So we can link to N from P to V, link through this path. Okay? And then this relationship have the function with this one. Okay? We have the overlap. The overlap is what? Your SV, which one is SV? I forget. forgot. But doesn't matter, okay? Anyway, so we use SV as a pair, okay? But in order to include the SV pair, we have two, we can go through this one, we can also go through this one. This is the overlap part, right? And then this becomes one pair. Then from that one is a P as V. So we write partial P, partial S, and the V is a constant. We write it that way. And this one is a TVS. Then this is a partial T, partial V, S, okay? And you can see the direction, P and V, this is positive direction, and this follow this direction, so this one is positive. And this T to S, T to S, the positive direction is defined as S to T, but this one is the opposite direction, right? Then we add a negative sign here. Check this one, PSV, PSV, and TVS. This is the way. You can try something else, okay? You can also try this one, PV, PTV, and then SVT. Just try it. You can get the relation. And then you use that pair, you have that one, use that pair. So this is how you memorize. But honestly speaking, I do not use that method. Okay? Every time when I want to use, I starting from this part and rederive it. Okay. Spend some time when you go back home. First